In this video, we will learn how to identify an excess of a reagent and limiting reactants in stoichiometric calculations. So before we start with this, there are two equations that you must know for stoichiometry, and these are N equals concentration times volume, and N also equals mass over molar mass, where N is equal to the number of moles. So let's start with the first example. In the first example, it says 100 ml of 0.1 mole per liter copper sulfate solution is mixed with 50 ml of 0.4 mole per liter sodium hydroxide solution. So in order to identify the excess and limiting regions, we need to go through three steps. Firstly, we will calculate the number of moles of the reactants that are mixed using what is given to us in this problem, and then we will compare the mole ratio of reactants mixed with the reacting mole ratio from the equation. And the difference in these mole ratios will indicate the excess and limiting regions. So let's start with step number one. So we will calculate the number of moles firstly of these two reactants in this equation. So the number of moles of copper sulfate first. So we are not given the number of moles, but we are told that 100 ml of 0.1 mole per liter copper sulfate is present in solution. So we are given the concentration and the volume, which we can use to calculate the number of moles. So N equals the concentration times volume, which is equal to 0.1 mole per liter times the volume. We are told that the volume is 100 ml, but for this equation we have to convert this to liters. So 100 ml is equal to 0.1 liters. So 0.1 times 0.1 is 0.01 mole. So the liters at the top, at the bottom, so this is mole per liter, and the liter at the top cancel out, so we have 0.01 mole. And now we will calculate the number of moles of sodium hydroxide that are mixed together. So for this example, we are told that in a solution there is 50 ml of sodium hydroxide at a concentration of 0.4 mole per liter. So again, we will calculate the number of moles using the same equation, N equals CV, which in this case is equal to 0.4 times the volume. 50 ml is the same as 0.05 liters, and this times by 0.4 is equal to 4 times 5 is 20. This is equal to 0.02 mole. Now we have calculated the moles of copper sulfate and sodium hydroxide that are mixed for this reaction. Now we can compare these moles in a ratio. So we have 0.01 mole of copper sulfate to 0.02 mole of sodium hydroxide, as we calculated here. Now this is the same as saying that we have a 1:2 ratio of both the reactants present. Now this mole ratio that we have calculated here is the mole ratio of the reactants mixed. Over here in this equation, we are given what we call the reacting ratio. So the reacting ratio refers to the coefficients that are present in front of the reactants. So in front of copper sulfate, we have 1, and in front of sodium hydroxide, we have 2. So the reacting mole ratio is 1 to 2. So the coefficients in front of the reactants indicates the reacting mole ratio. So, as a general rule, if the reacting mole ratio is the same as the mole ratio of the reactants mixed for this particular experiment, then both the reactants are entirely consumed in the experiment and we have no excess reactant. So in this case, the mole ratio of the reactants mixed, as we calculated from the information given, the mole ratio of the reactants mixed is the same as the reacting mole ratio as it is given in this general equation. This means that both the reactants are consumed in this reaction and we have no excess reagent or a limiting reagent. Now we will do another example which does have an excess reagent and a limiting reagent to see how we can identify that when the mole ratio, the reacting and the mixed mole ratio is different. So we will start again with the same method. So the reactants in this equation include zinc and this copper nitrate. So let's start with zinc. So what's the number of moles of zinc? We are told that 2 grams of the zinc metal. This is all the information that we are given. So how can we calculate the number of moles of zinc given the mass? Using this equation. N equals mass over molar mass. So we are told that there are 2 grams of zinc in the solution. And if you look at the periodic table, then you will notice that the molar mass of zinc is 65. It's 65.38. And 2 divided by 65.38, if you calculate that, this equals 0.03 moles. So grams cancel out, grams over grams per mole. So grams cancel out and the mole goes to the top. We have 0.03 moles. Now we will calculate the number of moles for the second reactant that we have for this equation, copper nitrate. So for this one, we are given the volume in solution and the concentration in solution. So we will use the equation that we used for the previous example, N equals CV. So the concentration is 0.1 mole per liter, and we times this by the volume in liters. So 100 ml is equal to 0.1 liter. So this is in moles. If you can understand my handwriting, moles per liter. The liters cancel out and we have mole in the end. 0.1 times 0.1 is 0.01. So the mixed moles that have been mixed for this experiment are 0.03, 0.01. These are the moles of the reactants mixed. This can be written as 3 to 1. So this is the mole ratio of the reactants mixed. Now we will use the equation to measure the mole ratio of the reactants, of the reacting mole ratio as given in this equation. So the coefficient in front of zinc is 1 and the coefficient in front of copper nitrate is 1. So the reacting mole ratio in this case is 1 to 1. Now we see that there is a difference between the reacting and the mixed mole ratio. In the mixed ratio, we have 3 times more zinc present, which means the zinc is present in excess. And so for this reaction, the copper is the limiting reactant. So this is how we can use the number of moles and compare the reacting and mixed mole ratios to calculate reactants that may be present in excess and those that are limiting the reaction. So this reactant, this zinc in excess, is not entirely consumed in this reaction, but we notice that copper nitrate is present at a lower ratio, it's present in a lower quantity, which means that unlike zinc, this reactant, the copper nitrate, is entirely consumed in this reaction. So the one that is entirely consumed is the limiting reactant. Thank you for watching.